In the last video lesson, we talked about hybridization and introduced you to the concept, and we're going to continue with the concept in this final video for topic 7. We're going to primarily be looking at the hybridization when it comes to multiple bonds. Now, the hybridization itself is actually going to be the same as it was in the previous video. It's going to be based on how many electron domains are around the particular central atom. However, what we're going to be looking at in this video is we're going to be looking at what happens when we have a compound that has multiple bonds. What does that bonding look like, and how do we show that using hybridization and valence bond theory? So let's take a look at an example of a molecule that has a multiple bond. So we're looking at C2H4 in this video, or in other words, we're looking at ethane. So to figure out what hybridization is needed, we're basically going to employ the same tricks that we've used in the last video with the hybridization. So we actually have two central atoms here. We have the two carbon atoms that serve as a central atom. And so we need to figure out what hybrid orbitals are needed. Okay, so we're going to do the same thing we did before, which is we're going to look at how many electron domains. So if I take a look at this carbon right here, how many electron domains are around that carbon? And the answer would be 3. There's the 1, 2, and then 3. Remember, double bonds and triple bonds both count as just one electron domain. Same thing for over here. If I were to look at this carbon atom, I have 1, 2, and then 3 electron domains around that carbon. And then so again, 3 electron domains there. So if I think about what hybrid orbital is needed for 3 electron domains, that's going to be sp2. So it's sp2 that's around this carbon atom. And then same thing for the other carbon atom, it's also going to be sp2 hybrid orbitals. So nothing new has really happened here, other than when we're counting electron domains, just reminding you that double bonds and triple bonds, you're just going to count as one. Now this video is hopefully going to explain why we do that and why we only count it as one. Okay, so let's go ahead and talk real quickly about what happens when you have multiple bonds. There are two types of bonds that are going to be going on here when we talk about multiple bonds and hybridization. We don't really need to go too in depth about what this stuff means. Further chemistry courses will do that, but basically bonds that are made using hybrid orbitals like the sp2, sp3, and so on are called the sigma bonds. And here's the Greek symbol for sigma. Okay, kind of looks like a letter O, just kind of with a little extension on it. And then bonds that are made using remaining p orbitals, so notice it's not hybrid orbitals, but it's just straight up p orbitals overlapping each other. These are going to be called pi bonds. And you might want to note in your notes that pi bonds is what's involved when you're dealing with a double or triple bond. Okay, so let's take a look at ethane again, but now in terms of sigma and pi bonds. So on this screen, I want to accomplish two things. The first thing I want to accomplish is literally being able to look at a molecule and determine how many pi bonds and how many sigma bonds there are. And then the second thing I want to accomplish is what does that bonding actually look like? Okay, so first of all, when you are looking at a molecule and you're asked to find out how many sigma bonds there are and how many pi bonds there are, you're basically going to be looking at the lines or the bonds represented in the molecule. Okay, easiest way is to first count how many sigma bonds there are. Okay, anytime you see a single bond here, 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 and here, those are going to be sigma automatically. When you're looking at multiple bonds, like a double bond, for example, the first line in the bond is also going to be sigma. Okay, so if I were to look at this molecule as a whole and I want to know how many sigma bonds there are 1, 2, 3, 4, and then 5, because one of those in the double bonds is going to be sigma. So total, there are going to be 5 sigma bonds in the molecule ethane. Now, how many pi bonds are there? Well, pi bonds only come into play when you're looking at a multiple bond. So the only time a pi bond is going to be coming into play is right here. And we already figured out that the first bond is going to be sigma, but any bond on top of that is going to be a pi bond. So of the double bond, one of them is sigma, so the other one must be a pi bond. And so therefore there is one pi bond in the entire molecule. Okay, so that's the simple really straightforward idea that we need to have behind sigma and pi. Now, the other thing, like I said, I want to accomplish in this slide here is I want to look at what does the bonding actually look like. Because if you recall on the first screen, these two carbons exhibit sp2 hybridization. Okay, sp2 here and sp2 here. So what do those sp2 hybrid orbitals actually do? Well, if you look at the carbons down here that correspond to the carbons up here, here's the atomic orbital of hydrogen. Okay, that'd be the 1s. And then here are the hybrid orbitals, the sp2 hybrid orbitals. The hybrid orbital sp2 overlaps there to bond with that hydrogen, there to bond with that hydrogen, and then the third one overlaps right there to overlap with the other sp2 on the neighboring carbon. So this overlapping right here is what causes the what we would say is the internuclear axis between the two carbon atoms. So that first line, which we already said was sigma, is because of those two hybrid orbitals overlapping there. And then same thing on this side. There's the sp2 and there's the sp2 there. So that just simply, you can think just bonds the single bond there. But then what causes the pi bond? Well, as you can see on these carbon atoms, there are also remaining p orbitals. So notice they're purple. They're not those hybrid orbitals. They're just straight up p orbitals. And there's overlapping here, which causes the pi bond. Now, I want you to note real quickly, sometimes students look at this image and they think, oh, there's two bonds going on here. So it actually should be a triple bond. That's not entirely correct. This is an entire p orbital. Same thing here. So even though it looks like it's two separate bonds, this is actually representing one bond or one overlapping between the p orbitals. So if you combine these two, the hybridized orbitals, as well as the hybridized orbitals making the sigma, and then the pi orbitals making from the p orbitals, this is what the bonding looks like overall. So all those oranges that you see here, 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 and here, those would be your sigma bonds. And then right here in the purple, that would be your pi bonds. Okay, now, how do you figure this out using hybridization that we learned in the previous video? Well, let me go ahead and reduce this screen a little bit. Okay, let's go ahead and draw out the ground state configuration for the carbon atoms, which are going to be our central. And I'm only going to focus on one because obviously it's going to be the same for the other one since they're both carbon. Okay, so if I were to look at the ground state configuration, we have our 2s, we have our 2p, and if I were to fill those in with electrons, it's 2s2 and then 2p2. Okay, so this is the ground state configuration for carbon. Okay, now we already know something's up because according to this, the way we have it drawn here, there's only two bonding sites, and we already know it needs three, right? Because it needs to bond with the two hydrogens and then the carbon next to it. So it needs three bonding sites. Okay, so what happens is it's going to do its promotion. Okay, so let me go ahead and draw that over here. Okay, so there's the 2s. And the 2p, and what's going to happen in the promotion is this electron right here is going to move over here. And so as a result, this is what we're going to look like after we have our promotion. Oh, there we go. Okay, so this over here is the promoted state of the carbon atom right here. Now, you may be thinking now, well, wait, what's going on here? Because, okay, yeah, we only had two bonding sites, but now we have four, and we only need three. We need 1, 2, and then 3. And not only that, but we've already figured out that it's sp2 that we need. Why would we need sp3? Well, you're right. We only need sp2, right? So if I were to look at the hybridization or the mixing of the atomic orbitals, okay, it's going to be s and then only 2 of the p's right there. So these 3 orbitals right here, the s and the 2p, those are the ones that actually would mix to create the 3 hybrid orbitals that are needed to bond to hydrogen, hydrogen, and then carbon. So what's left? What is this leftover electron right here? That's not hybrid. It's just straight up. It's the p. That's the electron right here that is left in this p orbital here. And you got to remember, this carbon right here is going to do the exact same thing. It's going to create the 3 hybrid orbitals here that bond to the hydrogen, and the carbon, but it's also going to have that 1 electron left over in the p orbital that's represented right here. It's those orbitals that are in the p that overlap to create the pi bond. Okay, so let's look at one more example right here to hopefully see what I'm talking about. So here we have carbon-carbon triple bond actually, and then 2 hydrogens here. So let me go ahead and minimize this so we can kind of have a little bit more room. There we go. Okay, so just without even looking at any hybridization, promotion, or anything like that, let's just look at how many electron domains, how many electron domains are around these carbons here. Okay, so around this carbon, how many electron domains are there? The answer there is there are 2. Okay, you've got the 1 right here, and then you've got the 1 right here. Remember, multiple bonds only count as 1. Same thing for the other carbon. The other carbon also has 2 because it has the triple bond here, and then it's got the single bond here. So according to our valence, I'm sorry, not our valence, our hybridization, 2 electron domains would be sp2. And so there would be sp2 around this carbon, and then sp2 around this carbon. All right, so let's look at what that bonding is going to look like. So I'm going to draw out, once again, okay, I'm going to draw out the configuration, ground state configuration for just one of the carbons, because they're both going to look the same. So let's look at this carbon right here. So the ground state configuration, just like on the previous screen, we have our 2s, and then we have our 2p. Oops, that's a bad looking p. There we go. And then we've got our 2 electrons there. That's the 2s2, and then we have the 2p2 right there. Okay. Now, you may think, oh, well, wait. Carbon only needs 2 bonding sites, 1 to this hydrogen and then 1 to this carbon. So why would we want to do any hybridization? Well, if we only do the 2 bonding sites, carbon would actually not have its octet satisfied. If it bonded a single bond to hydrogen and then a single bond to carbon, this carbon would only have 4 electrons, 2 here and then 2 here. So there has to be something more. And according to the Lewis structure, we can see that something more is this multiple bond here. So we've got to do a little rearranging. So we're going to still do an electron promotion here. Okay, so I'm going to go ahead and draw that actually below here. So after we have our electron promotion, our ground state configuration is going to look like this. We're going to have 1 electron there, and then 1, 2, and then that electron goes there. Now, we've already figured out that the hybridization we need is sp2. All right, so we know that the only hybridization, or the only mixing of orbitals that we're going to see, is between the s and then also only 1 of the p orbitals. So right there. That's the hybridization. And so once those 2 orbitals mix, it's those 2 bonding sites right there that bond to the hydrogen and then create the 1 bond right there. But then what do we do with these 2 p orbitals here, each one having 1 electron? Well, that's what you see here. Here's 1 p orbital, and then here's the other p orbital right here. There's 1 electron in this orbital, and there's 1 electron, there's 1 electron in this orbital. If I were to do this carbon's configuration, it's going to be the exact same thing over here. So you're going to see that it has the 2 hybrid orbitals, 1 to bond to the hydrogen, 1 to bond to the carbon, and then it's also going to have the 2 p orbitals left over. 1 has 1 electron, 1 has the other. It's the overlapping of those p orbitals and then the overlapping of these p orbitals that creates actually 2 pi bonds. Okay, so we actually see 2 pi bonds that are getting bonded here. And so if I were to ask you on a test or a quiz, how many sigma bonds and how many pi bonds does this molecule have? Let's go ahead and count it up. Remember, for sigma bonds, first count your single bonds. So there's 1, 2, and then if you have any multiple bonds like here, the first line will represent another sigma bond. So total, there are 3 sigma bonds in this molecule. How many pi bonds are there? Well, pi bonds are going to be looking at the multiple bonds, The first one we know is sigma. Anything on top of that is going to be pi. And so in a triple bond, the first one's sigma, but the other two would have to be the pi bonds. And that's what we see here in the picture. And so there would be two pi bonds in this molecule here.